Welcome, ladies and gentlemen, to some Integrated Math 2. In today's episode, we will be discussing special right triangles, beginning with the 45-45-90 right triangle, otherwise known as the Isosceles right triangle. Before we do any problems about this, I want to explain the anatomy of a 45-45-90 right triangle. It's also known as an isosceles right triangle because, as you guys know, an isosceles triangle has two sides that are going to be the exact same length, and one of the consequences of that is that the two base angles will also have the same measure. So the reason why this is known as an isosceles right triangle here on the left side is because if these two angles, or rather if these two sides are the same, then it stands to reason that the angles that are opposite would also be the same. So how does that tie into the title of this triangle? Well, remember, there are only 180 degrees possible within a triangle, and if 90 degrees are being occupied already by the right angle right here, and these two angles are cut in half directly, that means that you only have 90 degrees to be split between these two even angles, which means one's got to be 45, meaning the other has to be 45, hence the name 45-45-90. So you'll hear me alternate between the titles, 45-45-90, isosceles right. They actually mean the same thing, so please do not get confused when I reference them either way. If I'm going to assign some measurements to these, what I'll do is I'll go ahead and assign 1 here, a length of 1 unit, just to keep things started off. Now, if this is 1 unit here, and this bottom horizontal side is the same measure as the vertical side, it stands to reason that this bottom side would also be 1. And if I wanted to solve for C, or the hypotenuse of this particular right triangle, what I would do is I would employ the Pythagorean theorem on it. And so what would that be? Well, remember, the Pythagorean theorem is a squared plus b squared is equal to c squared. In other words, the leg squared plus the leg squared is equal to the hypotenuse squared. So in the context of this problem, that would translate into 1 squared plus 1 squared equaling c squared. And if I was to simplify this out, this would become 2 equals c squared. So c would equal rad 2. So go and box them up right there. Let's try another one. If I draw another triangle like this, and let's say I gave different measurements this time. Let's say, again, for this to be an isosceles right triangle, the two sides have to be identical. So when I say change up the sides, if I change one side to say 2 instead of 1, the other side needs to be changed to a 2 also, because remember, look at the tick marks. The tick marks tell me that the sides are congruent. I'll go ahead and solve for c here as well. So what does that look like? Well, that's going to be 2 squared plus 2 squared equals c squared. That gets me 4 plus 4 equals c. C squared. So c equals rad 8. Now, ordinarily, I might just leave this as rad 8. That way I don't have to worry about simplifying. But in this case, I think simplifying would be a good idea. Rad 8 can break apart by radical into 4 times 2. And if I took the square root of both of those, because this radical 8 is being square rooted, the square root of 4 becomes a 2, and I end up getting 2 square root of 2 equaling c. So I think you might start noticing a pattern here. I'm going to do a third one, and then I'll do a fourth one, and then I'll do one with a really crazy number that I think you guys will start to see a pattern, hopefully. So again, another way I could display this in terms of without the tick marks that are on the sides, I could say, all right, cool, we're dealing with another 45-45-90 right triangle by simply saying that the angles here are congruent. By saying these angles are congruent, I'm calling this a 45-45-90 right triangle. So get used to seeing all the variations in these special right triangles here. So I'll go and call him 3. And if this side here is 3, this vertical side is 3, remember, the triangle is isosceles, meaning the horizontal side has to also be 3. And I'll go and call him c here. So again, let's just do this one more time, just like we always have. 3 squared plus 3 squared equals c squared. 9 plus 9 equals c squared. C squared equals 18. So we know that c is going to equal the square root of 18, but let's find out what that actually is on the side here. The square root of 18 can be broken apart into the square root of 3, the square root of 9 times the square root of 2. And the square root of 9 can become 3, meaning 3 rad 2. So that is my answer here. C is equal to 3 rad 2. And I think some of you guys are starting to see a pattern here. If you are, then you can go and fast forward to the next triangle. But I'll go and do one more example here. That way we can really hit this one home. And I'll go ahead and just do a fourth triangle here. So a fourth triangle. And again, I'll go ahead and identify the sides being the same. Remember, this is only going to work if you have a 45, 45, 90 right triangle. Now, some of you guys might already be able to tell what this answer is going to be. If you're guessing that c is equal to 4 times the square root of 2, I would tell you that you're absolutely correct. But how did I get that? Well, that's really 4 squared plus 4 squared equals c squared. 16 plus 16 equals c squared. C squared equals 32. So c equals rad 32, but again, rad 32 can be broken apart into 16 and 2 underneath square roots. The square root of 16 is 4. 4 rad 2 equals c. Now, that does not answer the question of how you got that so fast. So, let's talk about how we got that so fast. I'm going to switch colors here. Now, if you notice, in the very first special right triangle, our side lengths were each 1. And if you notice the number that's in front of the rad 2, technically it's a 1 right there. In the second example, if you notice the 2's were both sides, the rad 2 is being multiplied by a 2 here as well. If we did 3 on either side, then the rad 2 is being multiplied by a 3. So naturally, I think it makes sense to assume that with 4's being on our special right triangle, our isosceles right triangle, our 45, 45, 90 right triangle, then 4 would be multiplied by rad 2 also. So without doing the Pythagorean theorem, because squaring these numbers would be really, really painful, if I gave something like this last triangle here, and again, the tick marks identify the sides being the same. The square here identifies it being a right triangle, so we're dealing with an isosceles right triangle. 7,324, and I wanted you to solve for c, and while we're at it, why don't we go ahead and solve for x at the same time? Then, based on the pattern, you might be able to tell, well, the tick marks here are telling me that the sides are the same. So if this vertical side is 7,324, then the horizontal side must also be 7,324. And again, if I told you without a calculator, square both sides and then add them together, you could tell me, no, I don't want to do that. I know the special right triangle relationship, and this is going to be 7,324 times, you guessed it, the square root of 2. So in general, I will go ahead and delete the board real quick. In general, a 45, 45, 90 triangle, or 45, 45, 90 right triangle, or a isosceles right triangle, will have the following measurements. If this side is x, then the horizontal side, which is congruent, again, please pay attention to the tick marks, the horizontal side would also have to be x. And then to get the hypotenuse, we would take that leg, that x length, and multiply it by rad 2. So when you look up 45, 45, 90 right triangles on Google, you'll often see a diagram that looks kind of like this triangle right here. Sometimes people will put it in as a ratio, and they'll say x colon x colon x rad 2. And then some people will put down a 45, 45, 90. The significance of the angles going down here is that these are the angles, the 45 and the 45 and the 90, those are the angles that are opposite those sides. So from here, this is opposite side. So if you notice, opposite the 45 that's up here, because remember, if the sides are the same, the bases are going to be the same, the angle here is 45, it's opposite of the x. This 45 is opposite the other x. This 90 is opposite the x rad 2. So that is usually your diagram for a 45, 45, 90 right triangle. Okay, let's go ahead and clean up the board a little bit. I'll talk about the 30, 60, 90. And we are back with our second special right triangle, the 30, 60, 90 right triangle. There is no special name for this. It's not. It doesn't have a name equivalent to the isosceles right triangle. It's called 30, 60, 90 because that's what the angle measures are. This angle being 90, again, 90 degrees left over to split between the two angles. 160, that only leaves 30 for the other side. So the way the 30, 60, 90 right triangle works is it's similar in the idea of how the sides look when it comes to 45, 45, 90. Now notice a couple things. Notice how there are no tick marks. There are no tick marks on the 30, 60, 90 right triangle because one side will be clearly different than the other. Opposite the 30 will be the small side. And the reason why it's small is because opposite of a small 30-degree angle will be the smallest side of the triangle. Opposite the 60 would then be the middle side. The middle side, because 60 is the middle angle of the triangle, so it makes sense that the bridge that's needed to fill his opening would be middle-sized. 90 is the largest angle there. We call this the large side. And that is the hypotenuse by definition. The hypotenuse is defined as the largest side of a triangle opposite the 90-degree angle. So how do these ratios work? Well, remember, in the 45, 45, 90 right triangle, it went x, x, and then x rad 2. Well, in the 30, 60, 90 right triangle, it goes a little bit different. The small side is going to be x. The middle side, well, maybe I'll hold off on him. The large side is 2 times the small side. And the middle side, well, this is going to get a little weird. It's the small side times the square root of 3. So if I clean up this triangle here, a 30, 60, 90 right triangle's diagram would look like this. 60, 30 here, you would get x, x root 3, or 2x. Now, another variation of this is when they swap the positions of the 30 and the 60. Because it doesn't matter where they go. If I put the 30 here and the 60 here, this side suddenly becomes x. Because again, we're opposite the small side, opposite the small angle. Opposite the 60 is the middle angle. That would go the x times the square root of 3. And then opposite the 90, or the largest angle, would go 2x. So oftentimes what you'll see in a diagram in a textbook will be one of these two pictures right here. But if they gave it to you in a ratio, it would be x colon x rad 3 colon 2x. And again, just like the 45, 45, 90, this x is opposite the 30-degree angle. The x rad 3 is opposite the middle, or the medium, x rad 60-degree angle. And then the 2x is opposite the 90-degree angle. Well, where did these ratios come from? Like, did someone just come up with it and it just happened to work all the time? No, of course it didn't. There's always a proof, and I will go ahead and show you the proof in this video here. Let me go ahead and move this guy out of here. All right, let's take a look at the proof of the 30, 60, 90 right triangle side ratios. And so what I'm going to do is I'm going to actually start off with an equilateral triangle. To demonstrate this, we start off with an equilateral triangle. Now again, remember, an equilateral triangle has 3 sides that are all the same length, as well as 3 angles that are all the same length, making each angle 60 degrees. And for purposes of the proof, it's always easier to see each side length not as x, but as 2x. And you'll see why I'm doing that in just a second. I'll put him down here because I'm gonna do something with him in a little bit. So again, what am I doing here? I'm trying to create a 30, 60, 90 right triangle, which I don't have right now. I have a 60, 60, 60 non-right triangle. But what I can do is I can go to the top of this triangle right here and draw what's called an angle bisector. And the angle bisector will do two things. It will not only cut this angle in half, but it will also split this side down the middle. So the reason why I called each of these sides 2x is because each side can be considered x now. And this 60-degree angle that was at the top can now become 30 each. Now if I highlight this triangle here on the left side, you'll notice what the angles are going to be. They're going to be 60, 30, and the angle bisector is also a perpendicular line, so 90. So this is the creation of my 30, 60, 90 right triangle. So I will go and draw him. Yeah, I suppose I'll just draw him down here. Okay, so from here, remember the measurements. The diagonal side was 2x. He did not change. But the bottom side did change. He went from being 2x to a solitary x. He's just x by himself. So, off the cuff, do you see where some of these ratios are coming in? You see the x, and you see the 2x. It's already starting to happen organically. The only thing I need to worry about is what this vertical side is. And basically, your underlying question needs to be, what is up with this x rad 3? Where is that coming from? Well, we will find out in just a second. For now, what I'm going to do is I'm going to call him h. H for, say, the height of the triangle. By the way, remember, the angles still correspond. This is 60 degrees. It hasn't changed. This used to be 60 degrees until it was cut in half. It became 30, and this guy was 90. So what I'm going to do is I'm going to go and solve for h using the Pythagorean theorem. So what I'm going to do is I'm going to say x squared plus h squared equals 2x squared. Again, I'm using the Pythagorean theorem. I'm going to get h by itself. So I've got x squared plus h squared equals 2x all squared is 4x squared. From here, again, I'm getting h by itself. That's all I'm doing. I'm going to go and subtract x squared from both sides, move a little bit to the right. H squared is equal to 4x squared minus 1x squared is going to be 3x squared. And then I will square root the h to get h finally by itself. X will equal the square root of 3x squared. So from here, how can I break him up? Well, he can be broken up into the square root of 3 times the square root of x squared. The square root of x squared is normally speaking the absolute value of x, but we're talking about length sides of a triangle, so it's just going to become straight up x, which can then be multiplied by this rad 3, becoming x rad 3, which is actually in our ratio. So that is where the x rad 3 comes from. So what you want to get out of this by the time it's all done is you want to be able to know these ratios of your special right triangles. No matter where the 60 and the 30 are, know the 30, 60, 90 right triangle, and know the 45, 45, 90 right triangle. Stay tuned for the next video. I will do a bunch of examples of each, and I will talk about the consequences of knowing these ratios really, really well. I will see you in the next episode.